Hello, so today I will be explaining a little bit about stereochemistry, identifying asymmetric centers, chiral and achiral molecules. I'm going to give you some definitions and then we'll work through some examples of those. Stereochemistry, stereoisomers, when we're drawing them on paper or tablets or whatever it is, we're drawing them in their 2D form. So by, drawing them a little bit differently, with wedges and dashed marks, as we will do, it kind of gives us an idea of what they will look like when they are in their 3D form. In real life, they are in their 3D form, and that kind of affects how they behave with one another, how they can be used when it comes to drug manufacturing, how they'll interact. So it's not just something we learn, it's something that actually has real life applications. One example of this I'm sure you've heard of is thalidomide. Thalidomide was a drug that was used for nausea, but when it was in its other conformation, right, there's a stereoisomer of it, it actually was attributed to birth defects. So on one hand, it helps with nausea, that's great. On the other hand, it has birth defects, not so great. So again, that's kind of another reason why understanding stereochemistry and how it works is very important. So the first thing we're going to do is define what an asymmetric center is, and then what a chiral center is, and what achiral molecules are. So chiral versus achiral. An asymmetric center occurs when there's an sp3 hybridized carbon surrounded by 4 different groups. So this would be a very, very simplified example. We have 4 different colors. Let's say that this center black circle, this is our carbon, and it's connected to a hydrogen group. Let's say it's connected to an alcohol group, maybe a carboxylic acid of types, and then bromine or chlorine, right? 4 very different groups. This would be an asymmetric center. And with this, there is no internal symmetry, right? So if I rotate this will never be symmetrical to one another. I'm gonna insert a screen sharing of my iPad because I think it'll be easier to explain. But when it comes to chiral and achiral molecules, the biggest difference is that they either can or cannot be superimposed. So if I were to take, let's say, my drinks that I drink way too many of, pretend they're the same color, right? If my head was a mirror, you could put them on top of each other and they would be the same thing, right? Or, do the same thing. I have nothing of the same color is the problem. But if I were to put this can with this can, very similar, they're both cans. Very clearly, they are different. You can still see this one, right? They cannot be superimposed here. All right, so first, we need to do 2 things when we're looking at these problems. We need to determine if they are chiral or not, right? If they have chiral centers, and if they do, where those chiral centers are. So when I'm looking at chiral centers, personally, I like to start at the carbon that has something attached to it, right? I always think that's a good start because at least we know we have one of our 4 different groups. So if we start at this carbon here, carbon 3, right? Because it goes 1, 2, 3, 4, 5. Okay. We can see right off the bat that there is this bromine, right? So this is going to be one of our groups. So one group, check. Now, as you can see, there's 3 groups attached to this carbon that are shown, which means there has to be a little hydrogen hiding out here, right? To complete the octet rule. So hydrogen is definitely very different from bromine. So those are 2 groups we have, right? 2 groups. Now we're starting here. We're gonna go to the next carbon. So if you look at this carbon, we have a CH2, and then here we have a CH3. Okay, so this is one group to the side. Then here we have a CH2 and a CH3. All right, well, if you look at these 2 groups, sorry, I'm getting a little messy here, they're the same thing. And because they're the same thing, this compound cannot be chiral, right? We're just gonna write this, no chiral center. Sad. Okay. Now, let's go to a structure, pretty similar, Same amount of carbons with a bromine substituent. The only difference is that now it's on carbon 1, 2, 3, 4, right? It's on carbon 4, but we would actually go the other way, so it's on carbon 1, 2. Okay? So we're going to do the same thing here. We have identified that we have one of our, we're going to start at this carbon, and starting at this carbon we have a bromine, right? So that's one group covered, check. Again, thinking about that octet, we're going to have hydrogen here, right? So that's another one of our groups, check. Next to this carbon, I wish you could see my mouse, we have a group here, and this group is a CH3. Okay, so CH3 is different from bromine, is different from hydrogen. Boom, we have 3 out of 4 of our groups. Now let's go back to this carbon here, and let's look to our, I guess it's the left side, right? And here we have a CH2. Well, this CH2 is also next to CH2 and then a CH3, but regardless, this CH2 is different than this CH3. And that means we have 1, 2, 3, 4 different groups, which makes this a chiral center. We're gonna do chiral. Smiley face. Yay. Okay, next example. We have a carboxylic acid attached to a cyclohexane, so a 6-membered carbon ring, to try to identify if this is chiral or not. Now, as a trick with ring structures in general, if the ring is the same on all sides, right? There's only one substituent coming off, but everything else is similar. Whoop. There's no, double bond or, an extra alcohol group. Generally, this is not going to have a chiral center, right? Because on both sides of this ring, boop, it's the same thing, right? So there is this invisible symmetry just in the ring. But alas, we will go through it anyways. So starting here, right, because I already see 3 things. So let's see if these 3 things are different, right? And again, octet rule, we know that there has to be hydrogen somewhere. All right, so we see our hydrogen. That's awesome. So we got one group. Attached to this is a carboxylic acid, this functional group right here. Okay, that's awesome. So then we just have to find 2 more groups. But as I had mentioned, these are the same. And because they are the same, this is not chiral. Next. So we're gonna kind of think of the same thing here, right? We have this little center. We have our bromine, so that's one group. I'm just gonna go from the group. My voiceover got a little messed up, but we have our bromine, and then we have a CH3 group. So now let's look at the ring. This carbon, we have a CH2, CH2, another CH2. And then right here, we only have a CH, right? Because we have a double bond. That gives us one of those hydrogens, right? So we only need one extra hydrogen. So we have a CH. And then on the opposite side, we also have another CH. And because of this was me trying to show you where that hydrogen is. But because of this, that's CH2 to the left of that potential chiral center versus the CH below it to the right. Those are different compounds, different molecules, and for those reasons, this is a chiral center. But I don't know how I'm gonna edit this. We'll see. Great. So now we're gonna look at this 4th guy, right? So there's a couple carbons we could look at here, but I'm gonna start at this carbon, this little fella here, right? Because I see 1, 2, and 3 groups. So we might be able to, find a chiral center in here. So if we look at this group, we you know, again, we're going to have this little invisible hydrogen. So that's going to give us one of our groups. Then over here, right, we have this oxygen right here. So this is going to be its own, you know, separate group as well. So now we have 2. Then if we look here, we have a CH2 and a CH3. If we look here, this looks a little different, right? But it is actually the same. Despite having a wedge, it's a CH2 and a CH3. There's this, you know, little line of symmetry here, actually. So those are the same, and because they are the same, there are actually only 3 groups, and this does not have a chiral center. No chiral center. Cry. Let's start in this corner over here. Let's start on this carbon. This carbon, again, you got our invisible hydrogen here. I think maybe a highlighter would be better. So we have one group here, we have our bromine. We have another group here, which is our hydrogen. Then over here, this is a CH3. So that is our 3rd group. And then all of this technically could count as our 4th group. So this is a chiral center. But structures can have several chiral centers, right? So this is a chiral center EA. Let's see, because this has 3 groups attached to it, right? Is this a chiral center? Well, let's check this out. So there will not be a, you know, hidden hydrogen here because you have this carbon that is double bonded to the oxygen, right? So it already completes its octet. It's the rule. But if we look here, we have our oxygen group, right? So that's 1. Then we have another alcohol group, so that's 2. And then we have this group here, and that's 3. So because it's only 3, it can't be 4. There's not that hidden hydrogen. This is not a chiral center. So it looks like we just have this one chiral center. Oop, I erased it. Right here. Boom. So a few things to review. There's asymmetric centers, there's chiral centers, and achiral centers. Chiral centers cannot be superimposed, right? So if you were to split this, let's erase a little piece here, and then flip this over. Oh, that did not work how I wanted it to work. It's not gonna work how I want it to work. But if you were to move this guy over this way and flip it like a pancake, it would be non-superimposable. You would not be able to put it over itself, right? So that is why it is a chiral center. If you were to take this right here, if you were to chop this guy up, let's just go like this, and flip him like a pancake, this would perfectly fit on top, right? If you went down this thing, flipped them like a pancake, which is why it is not a chiral center, because there are not 4 different groups. It was helpful and not more confusing. There's different little tips and tricks. I really enjoy this topic. 1, because it's fun to draw out and kind of find the groups, and 2, because you can use your molecular modeling kit and kind of see not only if there are 4 different groups attached, but how they would, you know, flip onto each other. So, yes, thank you for watching.